Welcome to our new unit on atmospheric pollution. Now on to the science of stratospheric ozone depletion. By the end of this, please be able to explain the benefits of stratospheric ozone and how it forms, and then describe the depletion of it, and explain efforts to reduce its depletion. This section is going to have a lot of chemistry, so follow along carefully. We've seen that ground level pollution has shown to contribute a lot of problems in the natural world, and it basically exacerbates asthma and creates all these breathing difficulties in humans, and it even causes cancer. So now let's turn to certain pollutants in the stratosphere that have a substantial impact on human health and our ecosystems. In the troposphere, ozone is an oxidant, and it can harm a respiratory system in animals and damage a number of plant structures. But in the stratosphere, ozone forms a necessary protective shield against radiation from the sun. So it absorbs UV light and prevents harmful ultraviolet radiation from reaching us here on Earth. So the sun radiates energy at many different wavelengths, including ultraviolet. And ultraviolet wavelengths are further classified into three groups. They are a UVA, or low energy ultraviolet radiation, and the shorter, higher energy UVB and UVC wavelengths. UV radiation of all types can damage tissues and DNA from living organisms. Exposure to UVB radiation increases the risk of skin cancer and cataracts and suppresses the immune system in all humans. Exposure to UVB is also harmful to cells of plants, and it reduces their ability to convert sunlight into usable energy. UVB exposure can harm entire biological communities. For example, loss of total phytoplankton populations, the microscopic algae that forms the basis of the marine food chain, can basically cause a fishery to completely deplete if UVB is not under control. So the ozone in the stratosphere absorbs ultraviolet radiation by filtering out these harmful UVB rays from the sun. And it's easily confused with stratospheric ozone with tropospheric ozone, or like the ground level ozone that we've discussed in earlier sections. O3. So, however, the stratospheric ozone occurs higher in the atmosphere, where its ability to absorb ultraviolet radiation shields us from the sun. All right, so it's important. And how it forms is also quite interesting. So when solar radiation strikes this O2 molecule in the stratosphere, that's 10 to 31 miles above the actual surface of the Earth, ground level, a series of chemical reactions begin to produce a new molecule, O3, ozone. So the first step is UVC radiation breaks down the molecular bond that's holding the oxygen molecule together. So from O2, we add UVC and we get O and O, two separate oxygen ions. So this happens only only a few oxygen molecules at any given point. The vast majority of all the oxygen in the atmosphere remains in its O2 form. All right, so in the second step, a free oxygen atom, just O, produced is the first reaction encounters another oxygen molecule, another diatomic oxygen molecule, and that's how they form ozone. So that free oxygen meets another O2 and we get O3, hence ozone. Both UVB and UVC radiation can break a bond in this new ozone molecule, forming this molecular oxygen and this free oxygen atom once again. So we can have an ozone molecule. And so I just realized that equation's not on here. So okay, so then that cycle starts again. The the UVB and UVC radiation can break a bond in that new ozone molecule, forming molecular oxygen and that free oxygen atom once again. So thus the formation of ozone in the presence of sunlight is a subsequent breakdown of the cycle, and that can occur indefinitely as long as there's UV energy entering the atmosphere. But this is under normal conditions. And under normal conditions, and basically when the amount of ozone in the stratosphere remains at this steady state, this can happen. We rely on refrigeration to keep our food safe and edible, and on the air conditioning in our household to keep us comfortable when the weather's hot. And for many years, the same chemicals that made refrigeration and air conditioning possible were also used to host a variety of other things in consumer items like aerosol spray cans, and it also is part of the production of styrofoam. These chemicals are what we call chlorofluorocarbons, or CFCs, and they were considered essential to modern life and when modern life began, and producing them was a multi-billion-dollar industry. Well, CFCs were considered safe because they are both non-toxic and non-flammable. But as it turns out, these chemicals had an adverse effect on another part of the world in our upper atmosphere, the stratosphere, by promoting the breakdown of ozone. So what happens is these CFCs were introduced to a chlorine atom inside of the stratosphere, and when chlorine is present, it can attach to an oxygen atom in the ozone molecule, and therefore by breaking it down, breaking the bonds, between the atom and the molecule, forming this chlorine monoxide type of thing. So that's the O3 plus that chlorine atom that gives you ClO, that chlorine monoxide, and the O2. So the chlorine monoxide molecule reacts with a free oxygen atom, that O, that's floating around in the atmosphere, and then pulls that oxygen from the ClO to produce this free chlorine once again. So that ClO will react with that free oxygen atom in the atmosphere, and then it'll pull the other oxygen off, and you'll have this free chlorine atom and O2 in the stratosphere. So when we consider these reactions together, we see chlorine starts out and ends up as a free chlorine atom. In contrast, an ozone molecule and a free oxygen atom are converted into two oxygen molecules, a substance that aids in the reaction but does not get used up by itself is what we call a catalyst. And so a single chlorine atom can catalyze the breakdown of 100,000 ozone molecules until finally one chlorine atom finds another and the process stops. In this process, the ozone molecules are no longer available to absorb UVB radiation, and as a result, the UVB radiation can reach Earth's surface, and that's what harms biological stuff. So this process is a cycle. The ozone formation and the ozone destruction have occurred for many years, but the use of those CFCs and refrigerants that started in the 1920s, and the increased use of their presence since then, have basically just led to this rapid destruction of stratospheric ozone. And so now, after decades and decades of use, the effects are now becoming extremely apparent. In the mid-80s, atmospheric researchers noticed that stratospheric ozone in Antarctica had been decreasing each year, beginning at about 1979. Since the late 70s, global ozone concentrations have decreased more than 10%. So depletion was greatest at the poles, but it did occur worldwide, don't get me wrong. In fact, there was one study from 1970 that was done in Switzerland that showed this clearing of ozone. And you can see it here in this graph. So the ozone concentration from less to greater, and over 1970 to 2000, and I think it went up to like 2012. Your book says 2010, but it continued after that. You can see the measurement of ozone and how it just changed over that whole time period. So even though we see a rise and fall, overall there's a general decreasing trend from 1970 to 2011. In response to this decreasing in stratospheric ozone, there have been 24 nations in 1987 that signed the Montreal Protocol, and this was on the depletion of that ozone layer. It was a commitment to reduce CFC production by 50% by the year 2000. And this was a far reaching, lofty goal in which the global CFC exporters, which was the US, appeared in some ways to prioritize the protection of the global biosphere in the short term, even though we had a good economic self interest in it. But more than 180 countries eventually signed a series of increasing amendments to make the CFC limitations more stringent. And by 1996, in total, the protocol addressed about 96 of the ozone depleting compounds that were in production. Because of these efforts, the concentrations of chlorine in the stratosphere have stabilized. They're at about 5 parts per billion, and it should fall to about 1 part per billion by 2100. Now, I won't see that in my lifetime, but you might. The chlorine concentration reduction process is slow because CFCs are not easily removed from the stratosphere, and you know, basically we reached this record high of concentration in our atmosphere. So with this leveling off of chlorine concentrations, stratospheric ozone depletion should decrease from now on. And the number of skin cancer occurrences should also decrease.